Good afternoon, everyone, and welcome to today's webinar, Beyond Our Solar System, The Quest for New Worlds. My name is Nicole Walker, and I'm the Senior Manager Alumni Relations here at Griffith University, and it's my pleasure to be your host today. I'd like to acknowledge the traditional custodians of the lands on which we are meeting and pay my respects to elders past and present, and extend that respect to all Aboriginal and Torres Strait Islander people. Today's session is being recorded and a stenographer is providing live captions. To access these, please click on the link in the chat, and at any stage, any issues, just pop them in the chat and we will assist you. Today is a rare opportunity for us to hear from one of the most accomplished voices in astrophysics, Dr. Jessie Christiansen, a Griffith alumnus and chief scientist at NASA's NASA's Exoplanet Science Institute. Jessie is recognised globally for her groundbreaking work identifying and understanding exoplanets, those mysterious planets that exist beyond our solar system. She's a TED Fellow, a leader at the forefront of NASA's search for new worlds, and amazingly, she began her journey right here at Griffith, graduating with a Bachelor of Science in Advanced Studies back in 2003. In today's session, Jessie will share some of the most exciting discoveries being made, give us the basics from super Earths to star systems that challenge everything we know about the universe. We'll hear about new technologies, and we're also going to have time for questions at the end. So please feel free to type your questions in, and we'll get to as many as we can at the end. So now please sit back, enjoy, and be inspired as we welcome Jessie Christiansen. Hi, Jessie.
Hi everybody. I'm going to correct one thing that Nicole said. It's not amazing that I started at Griffith. It's inevitable that I started at Griffith. Griffith's an incredible place to be a scientist. So it's the one correction I'll make.
That's right. Thank you. And that is very true. One of many amazing graduates. All right, over to you.
Thank you. Okay, so I will move to here and go full screen. Does this look okay? Someone give me the thumbs up. Okay.
Yep, all good. Yep.
Thank you. All right. As I said, thank you everybody for joining us today. It's such a pleasure to talk to Griffith alumni about my work now, which, as Nicole pointed out, started at Griffith. She totally outed my age, though. More than 20 years ago, I was a student there. And in particular, I did the Bachelor of Science with Advanced Studies, which I really credit with starting my love for research, right? Like I had never had any research experience before. And the specific structure of the Bachelor of Science with Advanced Studies meant that every semester you did a research project on top of your coursework with a different professor. And that was incredible. I got to see all these different labs, learn all of these different techniques, like peek behind the curtain with all the grad students and postdocs. And it was very exciting. And it really did start my love of research and led me to where I am today. So as I said, it's a pleasure to be here. So let's talk about the work that I do now, which was not work that I started at Griffith, but it's work that I'm very excited about. So I narrowed my talk slightly from the whole of everything beyond our solar system to a specific question that's very important to me, which is the search for Earth 2.0, why we exist and how we're going to find it. Because guys, I think we're going to find it. So let me move on. So first, let's talk about what an exoplanet is. It's totally okay, Nicole, that you stumbled over that word a couple of times. We literally invented a new word for this because it turns out it was a brand new type of thing. So let's look at this graphic. This is a schematic, not to scale, of our solar system. So we have one star, our sun, in the middle. We have 8 planets. I know, Pluto's not a planet anymore. It still exists. And in fact, Pluto gets to be the king of its own bucket, which is dwarf planets. So we created a whole new category of planet just for Pluto and its friends called dwarf planets. Dwarf planets, there's roughly a dozen now of these that have been found. And we think that there's many more, which is partly why we created their whole own bucket. What else do we have in the solar system? We have minor planets, that's asteroids, comets, Trojans, everything bigger than a grain of dust that we've been able to detect and catalog in our solar system. And there's over 1 million things in the database of solar system objects. So space is really big and really empty. And there's a lot of stuff out there. a million things in our solar system alone. But what are exoplanets? Exoplanets are planets around other stars. So in Australia, we're so lucky having the southern sky. If you go outside and look up, there's thousands of stars in the sky. So let's talk a little bit about the history of looking at those stars. Okay, so 2,500 years ago, 600 BC, Greek philosophers were talking about this issue, whether Earth was singular or plural. Was there one Earth or many Earths? And this was purely hypothetical. They were just kind of, in their Greek philosopher way, throwing ideas around. But they were wondering, were there many Earths or just one? And interestingly, Plato and Aristotle actually argued that there was only one Earth, that Earth was singular and unique. So it's 2,500 years ago, we're already asking this question. Are there other Earths? Okay, fast forward 2,000 years into the Renaissance. The Renaissance was this incredible time for art and science and literature in the Western world, and in particular astronomy. Astronomy, the telescope gets invented. We start unlocking the secrets of the universe around us. So this is a quote from an Italian mathematician named Giordano Bruno. And this is the quote: "There are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our system." So this was before they had discovered Neptune, for instance. I think even before they discovered Uranus, I think they still thought Ceres was a planet at this point. They had just invented the telescope, guys. Okay. So Giordano Bruno was actually burned at the stake for saying this. I mean, he also said a bunch of other stuff about the church that he probably shouldn't have said. But one of the things that he was charged for at his trial was heresy in the form of saying that there were other suns and other Earths, because that was heretical to the Roman Catholic Church, who were in charge in Italy at that time. So in 1600, just 8 years after making this quote, Giordano Bruno was burned at the stake. So thankfully for me, exoplanets are not quite so hot a topic these days in that sense. Okay, so that's purely hypothetical, although Giordano Bruno does, in later writings, hit on the problem, which is that stars are really, really bright and planets are really, really faint. So the question is, how do we find them? How do we go from this amazing idea that there might be planets around other stars to actually detecting them? So this is now about 70 years ago, the mid-1900s. Otto Struve is an astronomer, and he sits down and he thinks about this for a while. And he says, what if we measured how fast a star was moving? And we can do this. We can actually take the light from a star and measure its spectrum and see how fast it's moving. What if we measured how fast a star was moving? Because if that star had a planet going around it, like our sun has planets going around it, the planets will pull the star around. So in our solar system, Jupiter is actually pulling our sun, is dragging our sun around the middle of the solar system with a period of about 12 years. So our sun isn't just like stationary in the middle of the solar system, it's actually getting pulled around by the gravitational pull of the planets. So Otto Struve is like, what if we did this? What if we measured the velocities of these other stars? Now, interestingly, he kind of does the math and he's like, this would work best for very, very big planets, like Jupiter-sized planets, that were right next to their star. So very, very, very close to their star, because they would induce the biggest pull on the star. And everyone's like, well, but how would you ever get a giant planet right next to the star? We know how planets form. We've got the solar system. Little planets form next to the star and big planets form far away from the star. This is crazy. This will never work. So this paper languishes for decades. Between 1952 and 1995, this paper has 7 citations. Since 1995, it has hundreds of citations, and let me explain why. In 1995, they found the first planet using this technique. The first planet around a normal star like our sun. Turns out, to make its star wobble, we measured the velocity, we saw it move, and it's one of these giant planets that's right next to its star. We're going to come back to these later in the talk, but this was super exciting. It was a brand new planet outside of our solar system that looked nothing like the planets in our solar system. And in fact, the Nobel Prize in 2019 was awarded for the discovery of this planet. So 40 years later, finally, this technique works. And so that's 1995. So that's 30 years ago. So what's happened in the last 30 years? This is an animation that NASA commissioned. So I'm going to play this. So every time the year changes at the top, we will see more planets appear. The color of the planet tells you how it was discovered, and kind of how big the circle around the planet is tells you the period of the planet, like how long it takes to go around its star. So 2003, this is when I graduated. This is when I got really excited about exoplanets. There were less than 100. And then in 2009, the Kepler mission, which we're going to talk a bit more about, launches. And you'll see the Kepler field jump out around here. There it is. It starts to get really, really populated. We found thousands of planets just in the Kepler field. Then we start this ecliptic plane survey. You can start to see these purple patches pop out. And then eventually in 2022, when we had this animation made, we hit 5,000 planets. So in 30 years, we went from one planet around one star, one exoplanet, to 5,000 exoplanets, which is pretty amazing. And it's been such an exciting time to be part of the field. So what have we found? So this is a plot. I think it's the only plot I'm going to show. So you guys need to stick with me. You're going to be good. So this axis shows the period of the planet. So how far away the planet is from the star. So the Earth is out here at 365 days, right? This is 100 days. This is 1,000 days. On this axis, I'm showing how big the planet is relative to Earth. So this is 1 times the size of Earth. So out here, 365 days, 1 Earth radius. This is the Earth. And these are the 4 solar system planets, Mercury, Venus, Earth, and Mars, that fit on this plot. So these were all the planets that had been found before 2010, before we launched Kepler. And so hopefully you can see that they look incredibly different from the planets in our solar system. They're almost all this hot Jupiter. So, you know, they're Jupiter-sized planets. Jupiter is 11 times the size of Earth. And they all orbit their star in just a few days, between 1 and 10 days, right? So this is, you took a Jupiter and you parked it right next to the star. So Mercury, which is the closest planet in our solar system, has a period of like 88, 90 days. So almost all of these planets are much bigger and much hotter. So we call them hot Jupiters because astronomers shouldn't be allowed to name things. But that's mostly what we knew. Since 2010, it now looks like this. This is filled in with thousands of planets in between the hot Jupiters and the inner solar system planets. And this has led to a revolution in our understanding of how planets form, where they form, how they evolve, and what might be out there. So what led to this revolution? It was this search for Earth 2.0. It was this question that's been driving us for 2,500 years. Where are there other planets like the Earth? So that question led to the development of the NASA Kepler mission. That's what this telescope is. This is a beauty shot, we call it, of the NASA telescope. This was a 1-meter telescope that was launched in 2009, 1-meter optical telescope. So this is like the size of a small van. And it had one goal, which was to measure the frequency of Earth-like planets. How common are planets like the Earth? So it stared at this one patch of sky, which is a bit difficult to see from Australia because it's in the Northern Hemisphere, but I think there's a certain time of year where you could probably pops just above the horizon if you're up in Queensland. So this is the Kepler field of view. So it was 10 degrees by 10 degrees on the sky. The moon is half a degree, so 20 moons by 20 moons. Lovely big patch of sky. And it had 200,000 stars in it that we looked at. Now, we didn't use the technique that Otto Struve suggested. We didn't use the radial velocity technique, it's called. We used the transit technique. So the transit technique, let me play this one. So this is an animation of a system called TRAPPIST-1. So this little tiny cool red star in the middle is the star TRAPPIST-1, and it has 7 planets orbiting it, 7 very small rocky planets that are the size of Earth and smaller. Now, these are so tiny that they don't actually make TRAPPIST-1 move much, right? So this technique of measuring the velocity doesn't work as well. But we're lucky. These planets are lined up just right so that from our point of view, they pass in front of the star and they block some of the light. So at the bottom, this is real data from the Spitzer Space Telescope. And what you're doing is measuring the brightness of the star with time, and you see these dips. And every time there's a dip, the planet is going in front of the star. Now, it's a very simple measurement. You're just measuring the brightness of the star over and over and over again, which is frankly one of the oldest astronomical measurements that people have been able to make. But you just need to do it exquisitely well, because these dips are 1% deep or less. Very, very shallow. So let's look at planet B. So every time planet B comes in front of the star, you get a dip. And so the distance between those two dips is its year. So if you were an alien civilization looking at the Earth, every 365 days, you would see a dip if you were lined up just right. And then the depth of the dip tells you how big the planet is. A big planet blocks more light than a small planet. So even though it's a very simple measurement, you've already got almost all the information you need. You've got its period, which means you know how far away from the star it is. And if you know the temperature of the star, you know the planet's temperature. And you've got its size. So you can start to make a guess as to whether it's a gas giant or an ice giant or a rocky planet. So the transit method is what we use with Kepler. Okay, so let's come back to Kepler's one question, the primary goal of the Kepler mission. How common are Earth-like planets? Now, I want you to look at this plot and think to yourself, did Kepler find any Earth-like planets? Unfortunately, this part of the plot is still really empty. We did not add any new planets down here. And I can talk a little bit about why. Mostly it's because stars turned out to be noisier than they thought we would be, and our sun is a pretty quiet star, turns out, relatively speaking. And if the star is noisy, it makes it hard to find those tiny little dips. But we found thousands of planets that were bigger and thousands of planets that were closer in. So what we do is something dangerous that scientists should never do, but we always do because it's very tempting, which is extrapolate, which is to take these planets and say, if this trend continues, which maybe it does, then there should be this many planets here. And if this trend continues, which maybe it does, there should be this many planets here. So if you do that, if you extrapolate in these two dimensions, you get something like 20 to 50% of stars like the sun having a planet like Earth. 20 to 50%. Now, I've tried to give you the caveats that, you know, extrapolation is problematic, but we think Earth-like planets are probably common, right? Like, there's no reason that we know of to believe that these planets like fall off a cliff and don't keep going out. We have our solar system planets, for instance, that we know the planets keep going. And we have no reason to believe that this population doesn't continue down because we have our solar system planets. So 20 to 50%. That's incredible because there are 10 billion sun-like stars in our galaxy. So 20 to 50% is 2 to 5 billion Earth-like planets, which we could not have told you 10 years ago or 15 years ago. So that's very exciting and one of the results I'm most proudest of being involved in. Okay, so no Earth-like planets. Or not. So this is a system called Kepler 452b. Now, this is the closest thing we think we found to an Earth-like planet. So it's orbiting a sun-like star, which is good because the sun is the only place we found life around so far. It's the right distance to be habitable. It's not too close. It's not too far away. It's in what we call the Goldilocks zone or the habitable zone, not too hot, not too cold. Now, it's a bit big. It's about 1.5 times, 1.5 times the size of the Earth. And that's where we start to get a little worried that it's not just a big rock anymore, but some other type of planet like a mini Neptune or something else that we don't have an example of. But if it's rocky, this is the best thing we've found so far in terms of a rocky planet in the habitable zone of a sun-like star. The problem with Kepler 452b is that it might not be there because the data that we found it in look very, very noisy and very, very much like other instrumental artifacts that we found in the data. So we give it about a 50-50 chance of being real. If it's real, it's the best thing we found, but it's not a slam dunk. I wouldn't get in my Tesla and shoot towards this planet yet. Another thing we found, and that there have been more examples of even since Kepler, are rocky planets, like this one shown here, in the habitable zones, the Goldilocks zone, of M dwarfs, which are a different kind of star. So remember I mentioned TRAPPIST-1 is this like small, cool red star. So those are called M dwarfs, and they're much smaller and cooler than our sun. So the habitable zone is much closer, which makes it easier to find planets in them than, for instance, Kepler around sun-like stars. So this is a planet called Proxima b This is Proxima Centauri, which is the closest star to us. If you leave our solar system, the first star you hit is Proxima Centauri, and it has a rocky planet in the habitable zone, which is wild, guys. The very first star you get to has a rocky planet in the habitable zone. In the background here, this is Alpha Centauri A and B. So Alpha Centauri is actually a triple star system. You guys know Alpha Centauri. It's one of the pointers to the Southern Cross. It's the leftmost. The furthest away of the 2 pointers to the Southern Cross is Alpha Centauri. So Alpha Centauri is a triple star system, 2 stars called A and B, and then Proxima, which is this third M dwarf that's quite far away. So this has a rocky planet in the habitable zone. And we've actually found a number of these, though, at this point, a number of rocky planets in the habitable zones of M dwarfs. The problem is we don't know if these planets are habitable. Now, M dwarfs, they're smaller and cooler, but they're actually much more active than sun-like stars. So, you know, when the sun like burps and does a coronal mass ejection, and we get aurora here on Earth, we get these beautiful light shows because we have our magnetic fields redirecting all of these high energy, high radiation particles from the sun. So imagine if that was happening all the time, and was even higher energy X-rays and UV. Like, you know, Queensland, guys, we're the melanoma capital of the world. We know that UV is bad. So these planets might just all be sterilized completely by the harsh radiation from their stars. We don't know. We truly don't know. And that might be a very anthropomorphic view of things, right? Just because we couldn't survive there doesn't mean some kind of life much more sturdy and radiation hard couldn't evolve there. It's just, you know, then we start to get more speculative. So we have found 14 of these so far, 14 rocky planets in the habitable zones of M dwarfs. But we don't know if any of them are habitable yet. So in terms of the search for Earth 2.0, we're still kind of at nada, unfortunately. Now, one of the things we're interested in is whether these rocky planets around M dwarfs have atmospheres, whether they're able to keep their atmospheres given that they're so close to their star and their star is so active. So this is what we're currently using to try and answer that question. This is NASA's current flagship mission, the James Webb Space Telescope. This is an animation of how the telescope unfolded in space, which was genuinely the most terrifying moment of most astronomers' lives, because this was I want to say $11 billion mission. It was the biggest thing NASA had done by a long shot, and it really had to work, and it has worked. It's been spectacular. But the James Webb Space Telescope is able to look at these planets and see if they have atmospheres, which is very exciting. So far, none of them do, but we haven't looked at all of them yet, so we'll see. Okay, now, just because we haven't found Earth 2.0 doesn't mean we haven't found a lot of very, very cool things. So I want to quickly walk through some of the interesting things we found so far after I do a time check. Yes, good. Okay, so no Earth-like planets. Sorry, still looking. Will be exciting when we find one. So what did we find? Okay, so I talked about hot Jupiters, right? These huge planets that are right next to their star that are heated up to hundreds, if not thousands of degrees. So this is an animation of one of the canonical hot Jupiters, HD 189733b. And now I'll pause for a second to just apologize. They're, you know, planets are super cool and we give them such rubbish names, absolutely rubbish. So this is HD 189733b. So this is to scale, like this is how close it is to the sun, to its sun. These are right on top of their stars. So this one, the star burped, it did a coronal mass ejection, it spat out a bunch of high energy particles, and the planet, which I will replay the animation, you can see the planet, a bunch of its atmosphere gets blasted away by this interaction with its star. And so HD 189733b, so it's about to do the burp, big coronal mass ejection happens, a bunch of stuff comes out, and you can see the atmosphere is getting blown away. So HD 189733b is one of our best studied hot Jupiters. We've been able to measure its wind speed, the atmosphere's composition, and the temperature profile of the atmosphere. And when you put all of that together, one of the things we know about HD 189733b is that it's raining liquid glass sideways constantly. Like when we say hot Jupiter, we mean really hot. So not your vacation destination. Okay, so hot Jupiters. They're super cool to study, but not habitable. All right, So coming down to the bottom of the plot, we did actually find a bunch of things that are the same size as Earth, right? So this is relative to the size of Earth. And we particularly found a bunch of things that have periods shorter than 1 day. So these planets are going around their stars in a matter of hours. This one out here is like 8 hours. That's how fast it's going around its star. Now, they get really hot. And what happens to rock when you heat it up? It melts. We have this whole category of thing called lava worlds. And so if you guys remember Star Wars, I love using Star Wars to illustrate these things because there's so many different types of planets in Star Wars. If you remember the scene on Mustafar where like Anakin and Obi-Wan and like, no, you have the high ground. It's a lava world. Guys, these are real. We found them. So this is an animation of a planet called Kepler 10b. Kepler, so it was discovered by Kepler 10. It was the 10th planetary system discovered by Kepler B. It's the first planet in the system because A is the star. So this is, again, to scale. Like if you're on the surface of this planet, how big the sun is in the sky, because this thing is orbiting, I think it's like 10 hours. It's so close. Anyway, so these planets are also tidally locked. They're so close to their star that one side of the planet is just always facing the star. The same way our moon is tidally locked to us. It's always facing us. So the side of the planet that's facing the star is just a lava, like a magma ocean. It's just we think it's just completely blasted, melted rock. This is a cloud of silicates getting blasted off the surface that we're flying through right now. And at this point, I'll say if you get motion sick, maybe close your eyes for like 10 seconds until I stop narrating, because we're going to do a flyover. Everything I'm showing is artists' impressions and animations. So we don't have real pictures of these planets yet. I'm going to get to the end when I talk about real pictures. Well, it's going to be exciting. But for now, these are just imaginings of what it would be like to be on a lava world. And we're going to do a flip at some point. So again, if you get motion sick, stop watching just for a second. And we flipped. Okay. So this is an example of a lava world, Kepler 10b. And we have found like a dozen of these too. So they're not rare. It's kind of fun. Particularly, I love that nature has more imagination than we do. That's always my favorite thing. Okay, we did find a bunch of rocky planets that aren't so hot that they've melted. We did find a bunch of warm Neptunes. So Neptune is about 4 times the size of Earth. So this is kind of Neptune on this plot. So Jupiter's up here, Saturn's here at like 8, Neptune's here at about 4. But interestingly, the most common kind of planet we found is in between. It's not a rocky planet and it's not an ice giant. It's something in the middle. So this still is an open issue in exoplanets. We call them super Earths or sub-Neptunes, depending on who you're asking for money. So this is a schematic of the sizes of the planets in our solar system. So here's Jupiter and Saturn, and that's Uranus and Neptune. Then there's a jump to Earth. Earth is 4 times smaller. And then there's Venus, Mars, Mercury. So there's that big jump between Neptune and Earth. And that's where the most common kind of planet is. So truly some of the most open questions and interesting questions right now are they just big rocks? And where do they stop being big rocks? Are they just mini ice giants? And where do they stop being mini ice giants? Or is there a third type of planet that we don't have in our solar system, right? And speculation, given what we know about the bulk density of these planets, is that they're ocean worlds, water worlds, with like 50% of the planet is like, not in terms of coverage, like the whole planet is water, but 50% of the total mass of the planet is water. That's one of it's a speculation, but that's also created a lot of hubbub about what habitability could mean, right? If you have a water world. The very first one of these found, GJ1214b, is nicknamed Kevin after Kevin Costner from Waterworld. Lots of exoplanets actually have nicknames because, as I said, the names are rubbish. Okay, so what else have we found? Let's go back to the Star Wars mill. So this is a classic scene from A New Hope, the original Star Wars, of Luke Skywalker on Tatooine, looking off in the distance at 2 suns setting. Now, I want you to remember, this is like the 70s, right? Like we're 20 years before exoplanets get discovered. And George Lucas has this incredible vision of all of these different planets and all of these different, climates and surfaces and configurations and architectures. Anyway, so he has Tatooine, which is what we call a circumbinary planet. It's a planet going around 2 stars. And now we have found about 16 circumbinary planets. We found 16 Tatooines. So this is an example that has 2 stars and 3 known planets so far. So the 2 stars are in the middle, and then orbiting those 2 stars at progressively further and further away are 3 planets. So this is super exciting. We actually found it. And, you know, again, remembering this is 20 years before planets are discovered and 40 years before this system is discovered. George Lucas even got the colors right. Like, look at those 2 stars. It's a yellow star and a red star. It's, I mean, visionary, so exciting. I think, you know, this is why Star Wars created so many astronomers, right? Just the imagination. Okay, so let's move a little bit now to the future. So Kepler, unfortunately, had a succession of hardware failures. And unfortunately, when things break in space, no one can hear you scream and you can't fix them, especially when your shuttle program is no longer running. So Kepler, unfortunately, in 2013 had to pivot to a different mission, and then 2018 had to be shut down. 2018, it just ran out of fuel, couldn't do anything anymore. There are James Webb, which is flying right now. There's a mission called Roman that's launching next year that I'm super excited about. But this, my friends, is the future of the search for Earth 2.0. It's called the Habitable Worlds Observatory. And it is what it says on the tin. It's a flagship mission that we hope launches in the 2040s to actually go and take a picture of an Earth-like planet. So let's talk about what that would look like. So in the US, every 10 years, all of the astronomers get together and they come up with a strategic vision for what they want to prioritize in the next decade. So this happened in 2020, and the #1 recommendation for space from astronomers in North America, which is I'll read this here. Inspired by the vision of searching for signatures of life on planets outside of the solar system, and by the transformative capabilities such a telescope would have for a wide range of astrophysics, the survey, the Decadal Survey, recommends that the first mission to enter this program, this is a technology maturation program, is a large, about 6-meter infrared optical ultraviolet space telescope. That is what is now called Habitable Worlds Observatory. A couple of years ago now, NASA formed the START, the Science Technology Architecture Review Team, and I was very lucky to be one of the 20 scientists chosen to be on this team to start developing this concept for this mission that won't fly for 20 years, but it's a long road. So yeah, for the last 2 years, I've been able to help design what this telescope will be and what it will do, and that's been an incredibly exciting and rewarding part of my career. So what will it do? Okay. So we've talked about a few different detection techniques so far. We talked about radial velocity, which is the wobble of the star as the planet's pulling it around. We've talked about the transit method, which is planets coming and blocking the light from the star. This is the direct imaging method, which is pretty self-explanatory. The idea is that you actually try to take a picture of the planet. So this is real data. On the left, I want to stress this a lot because it's so impressive. It remains so impressive to me, even a decade after this was taken. This is real data of 4 super Jupiters, so planets even much bigger than Jupiter, orbiting a star called HR 8799. So the star is in the middle. See this little yellow? That's not the real star. We've blocked out the star using a very, very special camera called a coronagraph, which blocks out the star. And we've tried to search as close to the star as we can with our telescopes. So this is data, I believe, from Keck, which is a 10-meter telescope on the ground. And you can see, you can watch, this is a movie. We made a movie of planets orbiting other stars. And when I sound impressed, it's because, you know, we talked a little bit about the Copernican revolution in the Renaissance, right? The telescopes and discovering. Galileo has these images. He sketched the moons of Jupiter, right? Those 4 big moons of Jupiter. He sketched every night the positions of those moons. And he used that to work out that they were all orbiting Jupiter. And it was like the first evidence that not everything was orbiting the Earth or the sun, right? Like that there were things orbiting other things. Revolution, I wish there was a stronger word even. It's so incredible. So this is this is that equivalent now, but for exoplanets, right? We were able to take a bunch of images over like an 8-year period and use them to create a movie and see the orbits of these planets. Now, they're super Jupiters and they're very young. So this system's only in the tens of millions of years old. Our sun is 5 billion years old. And they're so young, they're still glowing. They're still like, in the middle of, they're finishing off forming. So they're still giving off a lot of residual heat. And that's why we can see them. They're really big and really hot. So this is analogous to how hot Jupiters were the first things we found with the transit method, right? The bigger they are, the easier they are to see. The hotter they are, the easier they are to see. So this is for super Jupiters. Now, what we want is to do this for Earth. So this is a simulation of what Habitable Worlds Observatory might see. So if you took our solar system and put it, let's say 30 light years away, so not too far away, but there's, a couple hundred stars in that distance. So if you took our solar system and put it 30 light years away and looked at it with something like what we want to design for Habitable Worlds Observatory, this is what you might see. So you can see Jupiter super well, right? Again, it's really big. And so again, this is with a 6-meter telescope, but this is what going to space gets you. So this is a 10-meter telescope on the ground, and this is a 6-meter telescope in space. Space is where it's at, guys, because the atmosphere, I love it. I breathe it. I don't want to look at stars through it. It messes up your stars. So this is Earth, right? That's super, that dot there. And then obviously when you're designing something to see Earth, you want to kind of overshoot so that if it doesn't perform as well, you still get Earth, which is what we didn't do with Kepler. So here's Venus, right? Venus is just a bit interior to us in our solar system, and it's the same size and it's even brighter. So it's there, it's right there. So the idea would be to run this mission for like 5 years and make this movie, but for Earth-like planets, right? Not giant glowing balls of gas, little cool rocks. And even then, we don't even want to just take a picture. We want to, oh, where's my plot gone? Nope, there's supposed to be a plot there. The presentation is trying to make a liar out of me when I said there's only one plot. It's like, well, you don't get to see the second plot. If I just quit and then reshare. There it is. Okay, so here's the plot. So we don't want to just see the little dot, right? It's incredible, but that's not what we want. What we want is to look for life. We want to look for evidence that these rocky planets in the habitable zones of sun-like stars, the thing that we're looking for, the thing that we haven't found yet, has life on it. So what we want to do is take the light from that little blob and spread it out in wavelength and look for features of things like water and ozone and methane and oxygen and all of these good things. Now, we don't actually have a killer biosignature yet where we're going to look at it and be like, absolutely 100% there's life there. And that's part of our work for the next 20 years is to work out what molecule or combination of molecules would we see and be like, absolutely, that is 100% life. But we're really excited to build an instrument that will do that. So let me come to the end. So this is
sorry.
Yeah,
we couldn't see that. We couldn't see that plot. It didn't show up for us.
Okay, I apologize for that. It's a spectrum showing how methane and oxygen and carbon dioxide create different features in the light. So that the takeaway is we're looking for features of molecules that could be evidence of life. I see it on my screen, but now I see you're right. In the preview, I don't see it there. I don't understand why it's not showing up. Okay, I apologize. Okay, so coming back to, are you guys updating at all now?
We just can see just like a blank sort of blank.
I'm just going to reshare. Give me a second.
Okay.
I want you to get to see the end. All right. I don't know if someone wants to move that onto the screen. Thank you. All right. Okay, so now, yes, now you can see it. Okay, so coming back to this main question, the thing that we're excited about. This is a journey that we've been on for 2,500 years. And in our lifetime, we might get there. We might find an Earth-like planet around a sun-like star. Now, there's still a lot of work to do, and this is still 20 years away. But I'm super excited to get to be part of this journey. I'm super excited to hopefully be there when we do it, when we find an Earth-like planet and look for life in its spectrum. And I'm super grateful to Griffith for putting me on this path in the first place. So thank you very much, everybody, for listening. And I'm happy to take questions.
Awesome. Thanks, Jessie. We've got, I don't know how many, count-wise, at least more than 10 questions in there to start to kick us off.
No
So I'll
worries.
just
Sorry for the
start.
technical difficulties. I'm not happy with that part.
That's okay. I was trying to wait to see if it was slow connection, but then it never came through. So, and I don't want to interrupt you because it's so interesting. So the first question is there an upper limit to the size of a rocky planet?
Yeah, so it's a good question. You can put the data, you can like play with the equations of state of different solids. We think at about 1.5 to 1.6 times the size of the Earth, you're so big that you're going to start accreting a very thick atmosphere out of the original dust and gas that the solar system is forming out of. So at some point, you just have this like runaway effect where you end up with this huge, thick atmosphere. And then, at some point, we don't call that a rocky planet anymore. If it's got a very deep, thick atmosphere, you end up more like Uranus and Neptune. So you can technically have, we've found planets that are twice the size of Earth that have the density of rock. So we think that they're still rocky planets, but they're rare at that size. Usually a planet that's twice the size of the Earth has much more gas than rock. So it's about 1.5 to 1.6 where it's about 50-50. So, there's a transition region between rocky and not rocky. It's not like an exact cutoff.
Thank you. And how collaborative is your industry between organizations around the world?
Oh, yeah. So, most of NASA's big flagships these days involve international contributions. So the James Webb Space Telescope, which I mentioned, has 4 instruments, and 2.5 of them are international contributions to NASA. So like NASA built the spacecraft, but the instruments that we're using to do these measurements came from other countries, and then they get to use the telescope. And there's the next big European mission for exoplanets atmospheres called Ariel has an instrument that NASA is contributing so that American scientists can be involved in that. So there are a lot of cross-pollinations and partnerships. So for Habitable Worlds Observatory, which I was talking about right at the end, we're hoping that Japan, who are interested, will come and bring an instrument and we'll work with them. So definitely the big international space agencies try to find ways to like leverage what they're good at to get involved in other missions, right? Rather than everybody repeat everybody's work, if this country is really good at building UV detectors, have them build UV detectors for everyone, sort of thing.
Awesome. Our next question is, has water and an atmosphere been found on any of the potentially Earth-like planets?
So, okay, potentially Earth-like is the trick there. So of those 14 rocky planets in the habitable zones of M dwarfs that I talked about, I don't believe there's any water yet. The most promising planet that has water is called K2-18. K2 was like the second phase of Kepler after its original hardware failures. So K2-18, the 18th planetary system found by K2b, the first planet in that system. You might have heard it. It's been in the news a couple of times. So it's one of these mini Neptunes. So it's smaller than Neptune, but bigger than the Earth. So it's in this kind of twice the size of Earth size range. But the density is the density of an ocean world, right? So this is one of these putative nuke types of planets that might exist. Now, the reason that's exciting is that's a lot of liquid water, and the only thing we know that all life on Earth needs is liquid water. So that's why we're excited. Now, it's very different temperatures and pressures than we have on Earth, so it's hard to know what that would mean, but we've seen water in the atmosphere. And the recent buzzy news was that people were starting to claim evidence of biosignatures like dimethyl sulfide and dimethyl disulfide, which on Earth are only produced by like krill in the ocean. So the fact that this is an ocean world and we see maybe evidence of these things. Now, the evidence isn't very strong, and there's a lot of debate right now about whether those signals are real, and if they're real, whether it's really a biosignature. But there is water on these planets, and we're hunting down the answers.
Awesome. And when you say that stars are noisy, what do you mean by that? Literally audibly noisy?
Yes, no, it's a good question. What I meant by that, we do think they're audibly noisy, but what I meant by that is that the brightness of the star is not constant, is not just a brightness like all the time. If you imagine, you know how annoying it is when the light bulb is flickering? Like stars are doing that all the time. If you measure them precisely enough, they're not just shining at the same brightness all the time, they're flickering, which makes it hard to find these little dips in brightness if the star itself is doing this. So there's lots of different time scales of this flickering. So one of them is that if you see these like high resolution animations of the surface of the sun is boiling, right? There's these like hot cells that bubble up and then cool off and go down. And that creates this like changing flux, changing radiation from the star. There are also longer term things like star spots, right? Like our sun has sunspots that kind of rotate in and out of view, and they change the brightness of the star. If you have a bunch of dark spots on the star's not as bright as if it's not spotted. So we see things like that as well. So there's like flickering on really short time scales, but then there's also these oscillations that are much bigger than the size of the planet signal you're looking for. So you have to do a lot of correction of the data to take out these signals and look for these tiny little planets.
Awesome. And the next question is, what happens when you find Earth 2.0?
Such a good question. If I'd had more time, I actually have a chunk of the talk that I like to give that I took out. This is a really interesting question, right? So there are examples in history of times when we thought something like this might have happened, right? So the two big examples I'll give are the War of the Worlds radio broadcast, right, from 100 years ago, where there was this radio play that was based on this book, War of the Worlds, where Martians invade. And there was this, perhaps apocryphal story, or at least highly exaggerated story, that people heard this and didn't know that it was a radio play and thought it was a real news broadcast. And there was panic and hysteria. Now, that was, an invasion. So that's different from just finding a planet. But that's like one way people could react, right, to discovering that there's a planet like Earth. Another way is, fast forward 50 years later, the WOW signal. So there was this radio telescope that was scanning the sky, looking for interesting things. And this one really coherent burst of radiation came out. And it's called the WOW signal because the person monitoring the output of the telescope wrote WOW in the margin because it was such a big signal. Now that one just inspired the most incredible curiosity. Even now, 50 years later, there are still like crowdfunding campaigns to try and like raise money and go and like look in that patch of sky again and see what we can find. We haven't found whatever it was yet, but it was super interesting. Now, in terms of Earth 2.0, it's such a fun thought experiment to think about what might happen. I think for perhaps even the majority of people, you're going to wake up tomorrow and open your newspaper or scroll on your phone and drink your coffee and be like, oh, cool. If you're religious and your cosmology, has something to say about Earth 2.0, that would be really interesting to incorporate that in. If you're a government and you're thinking about investing in space and space exploration, and suddenly you know that there are Earth-like planets out there, maybe you change how you think about that. So I think that there are a whole spectrum of possibilities, from nothing happens and no one changes to our whole understanding of our place in the universe upends many things about society, religion, government, personal beliefs, right? I wish I knew the answer to what it will do, but it's fun to think about.
There was a related question in there around what are the parameters to be able to make that definition or that announcement that Earth 2.0 has been found.
Yes. So this is also something that's kind of evolved with time, our understanding of this question. So for Kepler, which I have worked on for 15 years, Earth-like meant a rocky planet, which we now understand to be less than maybe 1.5 times the size of Earth, in the habitable zone, which, there are different people who draw different boundaries, but for us, it was between 181 Kelvin and 301 Kelvin, and the Earth is 273 Kelvin. So everyone can just add 270-ish to the current Celsius that you're at, and then you'll get to Kelvin. So Earth is like the base temperature, the equilibrium temperature of Earth is 273. So we actually think Earth is pretty close to the outer edge of the habitable zone. And then sun-like star. So that's the 3 criteria for an Earth twin, according to Kepler: a rocky planet in the habitable zone of a sun-like star. And, I was quibbling a bit because each of those boxes has fuzzy boundaries about what truly is rocky, what truly is a habitable zone, what truly is a sun-like star, right? Like how big, how small can you get and still be sun-like? So it's open for debate, but it's one of the things we need to define for habitable worlds observatories so we can talk about what success is, right? Like if you find a bunch of Kepler 452b's, which are maybe not rocky, did you succeed? So it's a really important question to nail down, and I wish I knew the answer.
Awesome. The next question is around AI, and how has AI changed the game for you?
Sure. So I would say one of the most important ways that AI has contributed to exoplanets is one of the things we do a lot is classify signals. So there are dips in the data, and you're like, is it a planet? Is it a second star? Is it a data artifact? Is it noise, right? So humans, especially at the start of Kepler, were doing a lot of manual classification, just looking at these light curves and being like, that looks like a planet, that looks like a star. You know, you can tell the software, look for a dip, and it's going to find every dip, but then you have to classify the dips. Now, classification is that's like AI bread and butter, right? If you give it a training set and say, here are 3,000 different examples of planets, stars, data artifacts, and noise, and then give it, here's 10,000 new pieces of data, can you classify these? It's going to do great. Like that's what it's written for. So for instance, I think it's like 301 new planets were found in Kepler data using a machine learning algorithm that was trained on the previous Kepler discoveries. And it just went back and looked at those 200,000 stars again. It was like, here's 301 planets you missed before. So that's really cool, you know, given that we've only got 5,000 planets, almost 6,000 now. So, you know, a goodly fraction of the planets we know are from machine learning. I would say the other area that it's good at is finding shortcuts, right? So, for instance, if you're trying to model a planet's atmosphere, an atmosphere, there's so much going on. There's 3 dimensions, there's pressure, there's temperature, there's phase changes, there's composition, there's clouds, there's hazes, there's layers. It's a very complicated problem. So when we're trying to model an atmosphere and match it to the data, it's very computationally expensive to try and like run a full up 3D hydrodynamic model. But again, if you have a big training set where you've done this a bunch of times, you can give that to the machine learning algorithm and say, okay, how could I have done this faster, right? Like now that you know all of the end conditions and these are the starting conditions, are there any shortcuts we could have taken? So finding shortcuts, especially if you've already done the hard work, but that means in the future, you know the shortcuts you can make, the approximations you can make. So classifications and finding shortcuts, I would say, are the really obvious ways that AI has helped. Totally separately, I'm on the publications committee for our society's journal, and we just had a whole extensive conversation last week about how AI will help, hurt, writing journal articles, which is really fun conversation.
A fun and tricky one, no doubt. It's
exactly
something that's similar here around assessment and student assignments and how they all need to be rethought, right, in certain disciplines to
indeed
protect academic integrity and allow students to show their knowledge. The next question is talking around different frames of viewing the world, I guess, and different histories that are depending what culture you've been brought up in. So the question is around why is it that astronomy is primarily taught from the perspective of Caucasian history when Indian astronomers knew the Earth revolved around the sun thousands of years? And then there's some comments in the chat around what different biases and things. But yeah, is that something that...
Sure. Yeah, I mean, I would say that it's, it suffers from all of the same biases that almost every field has of, the centers of the English speaking language that did it are the Western, Italian, Greek, Roman versions, and that those are the ones that have proliferated around the world and become the centers of learning. In my little timeline, if there was time and I could do the longer timeline, around 1000 AD, there's a Middle Eastern mathematician who has some really interesting things to say, kind of not dissimilar from Giordano Bruno about looking for planets out there. And there's a whole parallel timeline that has to do with planets and religion, right? So this philosopher is talking about how this Muslim philosopher is talking about planets out there and what that means for their religious cosmology. And then Isaac Newton actually has, just to bring it back to the white Caucasians, Isaac Newton actually has this really cool quote where he was actually devoutly religious. And he's like, God's just God of all the planets, right? There's other planets out there. God's just God of all of them. Like, there's no problem here. There's no inconsistency. So yeah, I would say astronomy is just not unique in that sense, and that there's been a lot of push in the last few decades to try and recognize all of these other places. I know, especially in Australia, I have colleagues who are really deeply interested in Aboriginal astronomy, right? Like these stories that were passed down for tens of thousands of years about the sky. And they were doing astronomy. It's not even just, cultural stories about the constellations. They were doing astronomy, right? There was, they were able to predict monsoon season coming because of the scintillation in the stars. They were observing the stars and seeing that the stars were changing. And this is upper atmosphere changes indicating the monsoon. They were doing astronomy. So it's really cool to see that that's, become more of a thing, right? To try to explore the true historic origins of some of these ideas.
Awesome. We're getting close to time, and there's tons of more questions in there, but perhaps you could let us know what is the most common question you're always asked when you're doing presentations like this, and what's the one question you want to be asked, and could you tell us the answer to that question?
One question I'm always asked. People usually ask why Pluto's not a planet anymore, which is partly why I've started front loading that in the talk. A question that I wish that I'm asked, I guess, people ask why. Astronomy is not cheap. I mentioned the James Webb Space Telescope, which is $11 billion. And Australia has a space agency now, which was very, that's only like 5 or 10 years old. And that's super exciting. But the Australian Space Agency budget is like $8 million a year, right? Like 1,000 times less. And so, I would just come back to the fact that, some of our oldest questions, some of the things that we've been thinking about since we have recordings are our cosmology, right? Like, are we alone? Where did we come from? Why are we here? Where are we going? And for me, astronomy is the answer to all of those questions, is this ability to search out there and find our place and understand our context in the universe. So for me, the why is really important. And, part of why I love what I do, I get to find planets around other stars. I have the best job in the world.
Awesome. Thank you. And for people, there's tremendous interest in the chat there, and a lot of people thanking you for the insights and how interesting the presentation has been. For people wanting to know more, where could they go? What sites could they follow or visit, or what are some next steps for people if they were?
Yeah. So, if people are interested in more of me blathering on about planets, I host a podcast out of Caltech called Explore Exoplanets, The Discoverers, where I interview people who found planets about how did they find a planet and how did they feel when they found a planet. And then we talk about what their favorite fictional planet is and whether we found anything like it so far. So that's fun. I'm on Blue Sky. I'm very rarely on Instagram. I have a website. If you Google me, my website comes up. There's a bunch of other outreach materials there if you're interested.
Awesome. Thank you. And
no worries.
We're going to have to wrap up now. Is there any other closing remarks you wanted to share with everyone before we?
Just happy anniversary, Griffith, and thank you for having me.
Awesome. Thank you so much, Jessie. It's been, wonderful, great session. Learned so many new words in the vocabulary, from hot Jupiters to the Goldilocks zone, lava worlds, the wow signal. Who knew stars were noisy, and so excited to hear about the Habitable Worlds Observatory, and congratulations for being selected to be part of that. And it's amazing to think. Exciting. To 2040, and all the work and discoveries that we've made in the lead up to that, and what that will bring to the world. So thank you so much for your time and your generosity today. We really appreciate it. And the shout out for the 50th anniversary, because it is Griffith's 50th anniversary this year, and we're so excited to be bringing the community together to celebrate this great milestone and the legacy and things that Griffith has been able to achieve, contribute and support to the world. So to wrap up, we've got a video that I'm going to throw to about the 50th anniversary. And then in terms of our webinars, the next one of this series will be on the 28th of August. And we're bringing it back to, don't know how to segue from finding new planets to personal finance, but that's where we're headed. So I didn't think that one through before before having to say that out loud, but that's what we're really looking forward to. That. So Professor Rob Bianchi is going to talk us through different decades, how you can be structuring and what you should be looking at to protect yourself and improve your financial health. So really hope you join us for that. Thank you again, Jessie. And we're just going to get Roxy, are you ready with that video for us to throw to? I can see it coming up here soon, I think. Yeah, here we go. All right, great.
50 years ago, it started as a spark. A bold vision to be a different kind of university, one that challenges tradition, creates new solutions, and confronts the social and environmental issues of its time. Since then, we've been building a legacy of innovation and impact, consistently turning ambitious ideas into lasting change, with every milestone reflecting the power of a university that dares to think differently. At Griffith, we don't just embrace change, we predict it. What mattered 50 years ago matters even more today. What began as a bold idea has grown into a global community of over 300,000 students, staff, and alumni. Our work is grounded in our values, making education accessible to all, respect for our natural environment, a dedication to social justice, and amplifying First Nations knowledge and culture. These principles define how we educate, lead, and connect with the world around us, reimagining what's possible in teaching, research, and engagement. Together, we'll continue to create a brighter future, one that benefits as many people as possible.